Hello and welcome to this lecture on analysis of variance, or ANOVA. After this lecture, students should be able to explain the application of a one-way ANOVA model, define the concepts of between and within total variance, calculate and interpret a test for two or more sample cases with means, and determine the significance of an F-ratio test statistic and interpret the output for ANOVA. ANOVA, or analysis of variance, allows for the comparison of more than two groups. In other words, ANOVA allows for the comparison of the dependent variable across two or more categories of the independent variable. When one IV and one DV are used, it is called a one-way ANOVA. So when we have one independent variable and one dependent variable, we're using what is called a one-way ANOVA. The assumptions for ANOVA are: independent variable must be categorical, right? We're comparing across categories of the independent variable, and the dependent variable must be interval or ratio level data. We have to have independent random samples, the population is normally distributed, and population variances across those categories need to be relatively equal. Next, we need to come up with our research null hypotheses as well as our alpha. Our research hypothesis is going to be that at least one mean is different from the others. Our null hypothesis is there is no difference in means across samples or categories of the independent variable. And like always, we're going to select an alpha value, usually 0.1, 0.05, 0.01, or even 0.001. Again, this is the threshold for statistical significance. Since we have more than two groups, we will have a lot of calculations. These calculations are not hard, but you will need to keep careful track of your samples and be consistent with your notations. There's two main calculations we're going to need to make. The first is between sum of squares, or SSB, and this is the sum of squared deviations between each sample mean compared to the overall mean, and it's going to measure the difference in mean between our groups and the overall sample. Within sum of squares, or SSW, is the sum of squared deviations within each group calculated between each individual score within that group and the group sample mean. Measures the variation in scores within a particular group or sample, in contrast to measuring the variation between different groups or samples. So let's look at between sum of squares. Between sum of squares is calculated by adding up n sub k, which is the number of cases in each sample, times the mean for the sample minus the overall mean for the data set squared. We're going to add all those up. Thus, if we have four groups or four values for our independent variable, we're going to have something that looks like the following: n1 times mean of 1 minus overall mean squared plus n2 times the mean for our second category minus the overall mean squared plus n3. You get the picture. And so we can quickly, if we have lots of categories of our independent variable, end up with a lot of calculations we need to make. Within sum of squares is the sum of each individual score minus the mean for that sample. And again, we're going to square that and add them up. So here we have yi minus the mean for yk squared, where yi is each individual score in that particular sample or category, and y sub k is the mean of that sample or category. This formula is fairly tedious, especially if we have hundreds of individual cases in each sample. Thus, we can use the following variation of the formula that tends to streamline things. Still is going to be a lot of calculations, and this is going to be the sum of each individual score squared minus the sum of all the sample means squared divided by the number of cases in each sample. It gets pretty complicated. Again, you have to work really hard to keep this straight. So again, we can use this alternative formula that is the sum of the squared scores for each sample. So this again is the individual scores for each sample squared minus minus the sum of all the scores in each sample divided by the number of cases in each sample. And so doing this, we can get the within sum of squares. Most of the time, we will have a computer or some sort of piece of software that will calculate this for us. Total sum of squares is going to be equal to the sum of each individual score in the sample minus the sample mean squared, and it's going to be equal to the sum of our between sum of squares plus our within sum of squares. This is the total variation for all categories or all samples. For ANOVA, we need to calculate 2 degrees of freedom. One for the between sum of squares and one for the within sum of squares. The between sum of squares is calculated as follows. K minus 1, where K is the number of groups, categories of the independent variable, and within sum of squares, which is going to be equal to the total number of cases minus the number of categories or samples. From this, we can then calculate the F statistic. And this F statistic is our test statistic for ANOVA. It is what we're going to use to decide if we have statistical significance or not. And we calculate the F statistic by looking at the mean square between divided by the mean square within. And that is again calculated by taking our between sum of squares, as shown here, divided by our degrees of freedom for the between sum of squares, divided by the within sum of squares divided by the degrees of freedom within. Again, it'll end up looking something like this if you were to combine all the formulas we've gone over so far. So as you can see, this can get quite complicated and there's a lot of calculations. So once again, if you're going to calculate this by hand, you're going to need to be very careful about how you do it, making sure you keep track of everything. The F statistic, or F ratio, is the ratio of between group variance to within group variance. Remember, we're dividing between sum of squares divided by within sum of squares, so it's going to look at the ratio of between group variance and within group variance. This means that a larger F statistic means that there is more between group variance than within group variance. An F statistic smaller than 1 indicates that there is more within group variance than between group variance. And we're always going to measure our F statistic as 0 or higher, but what we understand is that if our F statistic is less than 1, then we have more within group variance than between group variance, meaning there's more variation within each category of the independent variable than there is between the categories of the independent variable. Versus if we have a larger F statistic, it means that there's going to be a lot more variation between each group or each category of our independent variable than is in each category of the independent variable. So to determine the significance of our F statistic, we consult the table located in Appendix E. We're going to select the appropriate alpha that we chose, select the appropriate column based on our degrees of freedom for between sum of squares, also called DFB or DF1. Different tables use different notation. And then we're going to select the appropriate row based on our within degrees of freedom, or DFW or DF2. If our F statistic is larger than the F critical value shown in the table, then we know that there is statistical significance between your groups, such that there is a statistically significant difference between one of our groups and the other groups, and we will reject the null hypothesis. If our F statistic is smaller than the F critical value, then we know that there is not a statistically significant difference between our groups, and we will fail to reject the null hypothesis. That's it for this lecture. I hope it was helpful. I look forward to talking to you again in the future. Bye.